thanks for having me today. I'm Adam Mollenkopf. I'm from Redlands, California, just east of LA, so not too far from here. I come up here often, and I love to share some of the work that I'm doing with you today. So just to give you a little bit of background for the company that I work for a company called Esri. It's Environmental Systems Research Institute is what it stands for. We've been around since '69. Pretty much we're the founders of GIS, Geographic Information Systems, back in the day. A lot of the original folks that created GIS back then are still with our company, still leading our company, and putting us into the next round of technology that's emerging in the space. That's what I'm going to talk to you about today, is how we're building some modern applications for cloud-native solutions, delivering it as a SaaS product. And I'll talk to you about the technology underneath it and how we're using it, containers, stateful workloads, all those fun topics that Lisa was talking about a moment ago. We do have quite a wide installed user base. Since '69, we've acquired 350,000 unique organizations that license our software. With our SaaS products, we have a percentage of that are using our SaaS as well. So there's quite a wide adoption of our users. What I'm going to talk to you about today is give you an overview of the application that we're building for the SaaS to give you an understanding of what it is functionally that end users will do with it. And then I'll dive into the technology of it. So talking about, yes, sir?
Yeah, do you have your own computer system, or do you use something public cloud?
So the question was, do we have our own computer systems or do we use the public cloud? So we use both. So we don't host a data center anymore. Everything that we host for our SaaS is on public cloud. But our customers take our software and install it inside their on-premises environments as well. Yep, good question. Yeah, if you guys have questions as we go, just speak up or raise your hands, please. So I'll talk about the overview of our application that we're building, what it does for end users functionally. Then I'll get into more technical stuff, which I think is more of the focus of this session here. So I'll go quickly through the overview of the product, and then talk about the items and services that we deploy for each tenant, how they're containerized, and then specifically about stateful workloads. So just to give you a little bit of background to set the context for what I'm talking about with Internet of Things. Many of you probably are aware of this already, so I'll go through this quickly, but what we are enabling our customer base to do is to modernize their GIS applications, or geographic information systems, by connecting it up to devices that are out in the field. So it used to be that people would go out and collect data with a phone, snap a picture and say, there's damage at this site because of this natural disaster that just happened. Then they would cradle their device. At the end of the day, it would sync up, and that was the state of the art maybe 5, 6 years ago. In modern times, people want to be able to do that in real time, but they also want to be able to have sensors on the building itself to know that it happened as it happened, things of that nature. And so there's devices that are out in the field, and then there's also sensors that are attached to those devices, one or more sensors sensing things in the environment so we can understand what's happening in the environment. And then also some of the devices have the capability to actually be changed, so we can actuate events back out to the devices. And so if you look at a Gartner or a Forrester type of analysis of what an IoT solution consists of, these are the main components of that stack. And if you map it to what we provide at Esri, we map that quite well. So we have our SaaS platform, which is what we call ArcGIS Online. We have an application, which I'm going to focus on today, called Analytics for IoT, which allows us to do analytics both in real time as data is streaming in the ingestion path, as well as doing it after the fact, kind of the green box there, where we can look at the data after the fact. And we're using a lot of open source technology to do this: Kafka, Spark, Elasticsearch, all of those things, and I'll go through those in detail as we go through this as well. So the one thing we don't do as an IoT provider is device management, and so that's not our competency at Esri to do that. So we point our customers at folks like Azure or Amazon or other places to do the device management aspect of it. Now, Azure has its own kind of IoT platform as well, but it doesn't have deep geospatial type of analytic capabilities, and so we're in partnership with them to co-sell across our customer platforms, where an IoT customer for Azure comes to them, they need geospatial capabilities, we get referenced back to that customer, and we complement the IoT solution with our own geospatial things. Vice versa, if a customer needs device management or things out in the field, or even edge kind of computing out towards the sensors or the devices themselves, they use Azure or some other type of solution like Amazon for an IoT solution in that space. So it's very complementary, it's not a competitive thing at all. So about 6 years ago, Esri created a set of on-premises technology that enabled customers to do what we call real-time GIS. And so what that is being able to connect a GIS system up to real-time sensors out in the field. And so that's been an on-premises story for about 6 years now. We've got a lot of customers that have deployed that successfully, but it is quite an investment for those folks to do that. It takes between 5 and 7 machines to typically set up an environment like that. And it's quite an undertaking for our customers to set up. And so what we've been building recently, and what I'm going to highlight here today, is our SaaS offering of this. So the customer doesn't have to manage this infrastructure. They could just go and connect these things up to their environment. Now, 6 years ago, people were doing like 1 or 2 of these things. So like the city of Boston would track food trucks, or they would track their police department. And so they were tracking 1 or 2 of those things. And then they since, use it in the Boston Marathon for tracking the security officers and the police and the crowds and the anonymized cell phone signals and everything else that's around the safety of the Boston Marathon. And so they use it for lots of different things, but what we've seen more recently is folks like smart nations like Dubai and places like that are doing everything that's on the screen. And so they have all this velocity of data coming in from a wide variety of sources that are tracking all kinds of different aspects about their environment. And they need to have a geographic way to present that information on a map, not only just in real time, but also historically, where they can go rewind that kind of like a TiVo player and say, what did this look like yesterday? What did this look like 2 months ago? And so having this kind of film strip of data that they can go rewind and replay. What we're providing to our end users, and I'll be fairly brief with this because I want to make sure we have time for the techie talk, is the ability to configure feeds into the system. So this is a screenshot from the city of Atlanta that provides a citizen dashboard for their citizens to understand the current state of transit inside their city boundary. And so this allows them to visualize this directly on a map. So Esri provides base maps and other types of things as well, not just street data, but also kind of satellite data and other things like that. But we allow people to overlay those base maps with additional things like what you're seeing here with closed caption TV, transit systems. There's Waze alerts inside of this as well. And all of that's kind of culminating into a citizen dashboard that folks can use to understand their commute for the day. We also spend quite a bit of time to curate content for feeds that customers can use. So when they use our product, they can bring in things like wind speeds or earthquakes or fire parameters or live things that are happening out in the field. And so this enables them to bring in this content really easily. Once they brought in this content, they can detect patterns of interest and analyze things that are coming in. And so they can configure what we call these real-time analytics. These real-time analytics configure a series of analytic workflows, and then we can alert or actuate events back out to the IoT based on some patterns being detected. And then lastly, we can do big data analysis on this as well. So all of these, like if you look at this graph here, what gets compiled underneath this is a Spark streaming job. And that Spark streaming job will be scaled out appropriately to handle the velocity of data that's coming out for that specific feed. We also use Spark to do batch analytics. And so Spark is used here to do these analytic capabilities, but we've extended Spark with 20 or so user-defined functions that do space and time analysis. And so we can do things like find a hotspot. So in this case, we're finding the hotspot, giving anonymized cell phone data, find the hotspots of activity by hour of day of where emerging activities happen, and look at that over the course of many days and see where a hotspot is emerging or where a hotspot is declining. And so we can do all this scientific analysis about distribution of population, all kinds of other things. And we can schedule these to run on a periodic basis as well. So these are some of the analytic things that I mentioned. We extended Spark with analytic capabilities. So I'll just highlight a couple so you can get an essence of what our customers are doing. Reconstruct tracks and the summarized data would be, if I'm providing my cell phone location information as a volunteer piece of information, I could use that to reconstruct my tracks throughout the course of the day. So when I traveled here, I went from LA to San Jose Airport to here. That was, 2 different journeys that I took. And so I could reconstruct the tracks and draw a line of all my movement for the course of the day. But I could use something like calculate journeys to actually calculate the journeys between those locations. And so if you've ever gotten in the car and Google Maps tells you, are you driving home? They probably guessed that based on your pattern of life. And so these are very similar tools to that, where you can do pattern of life analysis and understand the probabilistic nature of, I'm probably going to be driving back to my hotel after this because I knew that I came from there, and I've done that on a frequent basis. So I'm going to show you a demo of our functionality, and then I'm going to jump into the technology behind this. So this is the SaaS user interface that we're providing to our customer base. These are feeds. I'm sorry that the screen's a little bit small. But a user can go configure a new feed. And so this could be, you know, connect to Twitter, connect to Facebook wall, or any of that. So what we're clicking into here is, we said I'm configuring a web messaging. So I could connect to a RabbitMQ, a Kafka system, anything like that. In this case, it's Kafka. And what we're doing is reading off of a topic that they just entered in there and sampling some of the data, trying to guess at a schema. If that Kafka had a schema registry associated with it, we would be using that schema, but in this case there wasn't one, so we made a best guess as to the types. The user, being a geospatial application, needs to configure what are the geometry fields in this case. So there's two fields, one for longitude, one for latitude, that's going to represent this data. And then I can specify, you know, a start and a date time for what's coming in. So oftentimes these feeds from a geospatial perspective need to know what's the geometry. If it's point data, could be polygonal data that's streaming in as well. And then what's the time aspect of that? So what's the most recent version of this? So a lot of times point data is what's coming in, but we can get other types as well. And so what I'm gonna do now is save this as maritime ships feed. And so what we're gonna be bringing in here is a global vessel feed. So there's about 100,000 vessels that report every second or so. And we can get that information presented on a map and do some analysis with it. So this is the feed that somebody's configured. They didn't need to go, you know, program a Kafka consumer or anything like that. We just kind of abstract that for them, and we provide them a feed type to connect to Kafka. And so now we have this maritime ships positions. It's started, and then I can do a series of other things with it. If I click back into it, I can open it in our Esri map viewer. And this is the map viewer. We zoom into North America here. What we'll see is we'll see some vessels starting to stream into the screen here. And so we simulated this data to make the vessels move a little faster than normal, because I don't know if you've ever sat there and watched vessels on a map, but they don't move very fast. So we thought we'd make it more interesting and make them move a little faster than normal. So I think they're going about 50 times faster than they normally do. What I can see here is there's a vessel type 1019, and that doesn't really tell me much. You know, maybe that's a code for a specific type of vessel. So one of the things I want to do in a real-time analytic, if I click into analytics here, is to create a new analytic. I can say I want a real-time analytic, and it's from an existing feed. I can point to that ship positions that I just created, that feed, and then I can create what's called a field calculator. It calculates a field, and it'll take those coded values and create, you know, basically a table lookup. And so I've already written a script to code all those things and codify them. And so we'll create an expression here. And so this is like an expression builder environment that people can code things into. So that's just codifying everything from the codes to a label that makes more sense. I can test the value here. And I can see that that's a recreational vehicle, that 1019 that was there. So this gives the users a way to easily configure this type of thing. I'm going to save this analytic. Again, what's being built here is underlying a Spark streaming application is going to get compiled. So we're going to take this directed acyclic graph that's here, and we're going to create a Spark streaming job. We're going to scale it out to the velocity of the data that's coming in, and then we're going to start processing events to come through here. But before I do that, I'm going to create another output, and I'm going to create a new layer that can be used on the map. And so this, I'm going to create a new layer, and I'm going to say, you know, save this as a new table, and I'm going to give it a name. And so what this will do is it'll store this. And so this is storing like cells of a film strip in our database so that we can go back and rewind the map and see what's happened over time. So every time a ship position comes in, we're going to calculate that field and we're going to write it to the database. We'll save that. Again, Spark streaming job is being created. We'll start that up. But before we do that, what we also want to do is filter some of the data. So we can filter the data spatially by using a polygonal data set. And so what we're going to do now is we're going to browse to our data sets that are inside our GIS. And we're going to say, find me the maritime boundaries that are in for this jurisdiction here. So a lot of times, you know, we may want to know where they're inside of maritime boundaries so that we can collect, you know, how much emissions were spread throughout, you know, this polygon. And so we'll find this. We're going to visualize that same data set that we put in there so we can see what it looks like. We'll add that to the map. And then we can see here's some polygons that represent the maritime boundaries in this case. And so what we might want to do is I might be interested in just the Bahamas and the Cuban economic zones here. So I might want to just filter for vessels that are inside those areas. So just Cuba and the Bahamas. And so given that set of polygons, every time a point comes in, I want to test to see if it's inside those polygons or not. If it's not, I want to filter it out. And so we're going to use a filter. And we're going to connect that ship data up to the filter, and we're going to filter it by that polygon data, so by space. And I can select what kind of spatial operation. Does it intersect? Is it disjoint? Does it cross? All those different types of things. And then we're going to create a new stream layer that's going to put the data on the map so that we can see the output of that filter. So we'll call this ships Cuba Bahamas and complete that out. And then as we save this and play this, what we'll see on the map is that we'll have a data set that has all the vessels in it that you saw before. We'll have the polygonal data sets, and we'll see just the Cuba Bahama data being streamed in. So we're starting this analytic. And if we go back over to our services, we'll see the analytic has been deployed. It's successful. It's running. And then it's running now. So we'll go over to the services, and we'll open this up on the map and see the output of what we just created. So this is representing real-time GIS happening. We'll search for the layers of what we just created with the ship data. We'll bring that in.
The ships have some type of responder on them?
They have a satellite transponder on them, yes. Yeah, so when they're close to shore, we have other communication mechanisms where we can get it more frequently, but when they're out deep in the ocean, it's a satellite transponder.
Can you talk about a little bit about how you collect all this information?
So we have
to a central computer system.
Yeah, so the question is, how do we collect all this through a central computer system? So we have providers that specialize in collecting and aggregating this data across the world. So ExactEarth is one of our partners that does that, and they collect all of the data off the satellites.
So it's just sent to you?
It's sent to ExactEarth, and we're using ExactEarth services to basically present this on the map. Yeah, okay. It's streamed in real time. So let me back this up just a little bit. So, so what we're seeing here is we have the polygonal data sets. We're going to make them a bit more transparent so that we can actually see the dots on top of it. So you can see kind of the cartographic control that we have. We can enable the pop-ups. We can set the layer up to refresh on a frequent basis so that we can see new things appearing. And then we can also, see the red ships that are coming in. And we can make the polygons more transparent so we can actually see through what's happening here. So these are some of the cartographic controls that we provide to users. And what you're seeing now is actually that there's an aggregation that's happening on the fly as well. So we don't want to see tons and tons of dots on top of each other. And so what we do when there's a certain threshold reached, we aggregate the data so that they can see what's aggregated. And the blue dots that are showing up now are just the ones that have been filtered. And we see now that there's that vessel type stream that was added. So now we're seeing that we got that codified label added to it. But we also have the Cuba and Bahama vessels filtered in, so we're not seeing anybody else. So that's kind of a quick overview of what the application does for our end users. So hopefully that'll give you a better understanding of the rest of what I'll be talking about here as far as what we're creating for our users. Sorry, I didn't mean to open Slack. Let's kill that. Okay. All right, so we have many tenants across multiple regions. And so within a region, we'll have thousands of tenants. And so what are we deploying for each of the tenants? So when we have a SaaS, we want to make sure that first we have good isolation. So we're not, putting customers in the same namespaces and other things right here. And so we wanted the most isolation possible. And the best way to do that is we're spinning up a Kubernetes cluster per tenant. So each tenant has their own cluster. So if you're organization 1 using our service, you get your own cluster. Organization 2 gets an entirely different cluster. And so that's what's represented on this diagram here. And so as far as the regions that we support around the world, we use Azure as our primary SaaS provider. But one of our principles also was to remain cloud neutral. So we wanted portability of our application as well. So we test just as well on Amazon as we do on Azure. We have a lot of defense and intel customers that use a private Amazon cloud infrastructure. So it's important for us, even though our SaaS is based on Azure, that we need to be able to deploy into those spaces as well. So having portability across Azure, Amazon, and in the future we'll be in the Chinese market inside of like Alibaba and other cloud providers there as well. So a lot of our design principles and open source frameworks and things that we use are based on having portability across these different cloud providers. Now, Azure, for instance, has multiple availability zones in the areas that have diamonds. So there's not a lot of those right now, so that's growing as we speak. But there's 3 pairings of those, and our qualifications for choosing a region that we would support is that there's 2 diamonds inside that availability zone that are geographically dispersed. And so for the US, we're primarily using West US 2. East US 2 is a backup disaster recovery site, and we're using West Europe and North Europe as a primary. We'll be expanding out to Asia and the Middle East as a next phase. And so our regions are these, but what's important is that we have backup disaster sites as well. So if for some reason, the West Coast gets annihilated, and we're probably not, any of us are alive, but the staff that I have on the East Coast could resume the clusters for them, and they have a disaster recovery plan in place. And so we have that kind of capability with us, having those different areas. And I'll get more into disaster recovery in just a little bit. What we also have is we have another Kubernetes cluster within each region that's the administrative cluster that manages all the other Kubernetes clusters. So it's kind of a kube and kube structure. So when we provision a new Kubernetes cluster, the admin cluster is provisioning it. It's also monitoring the health of all the Kubernetes clusters as well. So it's a federated type of model. So if we look at each tenant's cluster, if we put a magnifying glass on tenant 1 there, what you basically see is the 3 things that I just walked through in a demonstration: the feeds, the real-time analytics, and the big data analytics. Those are things that a user configures. The things that we provide as core services underneath that are the dark blue things. And if we took a technological view of it, this is basically the stack of software that we're using to pull it all off. So on the feed side, we use a combination of Scala, Akka, and Spark to bring in feed data, depending on what type of feed it is. We have 50 different types of feeds that connect to lots of different things. Connect to Kafka, connect to RabbitMQ, connect to Azure IoT, connect to Amazon IoT. There's feeds for each one of those. That is written into a Kafka cluster, and that Kafka cluster is backed by Portworx, which provides us the stateful resilience, which we'll talk more about later. Kafka comes along with the Zookeeper, which is the funny looking guy there. And then the real-time analytics that I configured are listening to a topic on Kafka. So each feed gets its own topic. The topic is partitioned appropriately based on the velocity of data that's coming in. And then those real-time analytics can write the data to our Elasticsearch database. Again, that's backed up by Portworx as well for stateful resiliency. And then after a certain data retention cycle that a user configures, they can say, I want to keep this data around for 6 months or 6 weeks. After that, we export the data out to Azure Blob. And Azure Blob can be used as a source for our big data analytics, or we can do big data analytics on the data that's inside the database as well. The data gets pushed out to the client through a stream server. So that's what was pushing those blue dots on the map. It's a WebSocket server. We call it the stream server. And that's based on Akka technology. And then we have a traditional web server that's based on Play and Scala code that's generating the map images and things on the server side that pushes images back to the client. We also have logging and monitoring infrastructure per tenant as well. So we started off with an ELK stack, the Elastic Logstash Kibana, but we replaced the Logstash with FluentBit. So I guess it's the ELK stack now. I don't know if that's a thing. And then we also on the monitoring side use the Prom stack. So Prometheus as a metrics gatherer. Each of our nodes have Prometheus are scraped to get Prometheus metrics, and then we use Alert Manager to alert operational staff if there's any type of issues with sizing or other things that need to happen. And then Grafana is used as a visual dashboard for all that information. We also have an auto-scaler set of things, and I'll cover that in a bit. So if we looked, and I apologize, it's kind of small font, a small screen, but if we looked at this topologically, that was kind of a logical view. What actually gets deployed, this is a container meetup, so I thought you guys would be interested in this level of detail. So if we look at the containers, we're using D16 VMs from Azure. That's a 16-core, 64-gig box. And so what that enables us to do is set up a number of things on them. All the things on the bottom here that appear are things that we use per node. So we attach a single 1 terabyte disk to this node as a starting point. And then we'll add up to 8 terabytes of storage for this node. And then depending on what container workloads land on that machine, that storage will get used faster or slower, and then we'll scale that appropriately. So we'll talk more about the scaling in just a little bit. But we start with 1 terabyte, and then we grow from there. We also run another daemon set that's Portworx. Portworx is the software-defined storage abstraction that enables us to have replication across the storage aspects of this. And so if I have an Elasticsearch data node, it's backed by a persistent volume. It's in Kubernetes, and that persistent volume is backed by Portworx. So if that Elastic node, data node failed and spun up on another node, I can pick up where I left off because that Portworx node is replicated across other machines, other nodes in that stack, and it can pick up where I left off without having to do a rebalance. So Cassandra, Elasticsearch, a lot of these things have rebalancing capabilities and they have replication built into them, but it makes it, we want a very deterministic environment when we're writing high volumes of data. Some of our customers are writing 3-4 million events per second into this thing. And so, if we're writing that many events per second into Elasticsearch, we need to make sure that Elasticsearch isn't going through a rebalance and there's this bad quality of service time where we can't keep up with that rate of data. So we want to avoid rebalancing at all costs. And so Portworx gives us an enabler for not having to do the rebalance. The other thing that we deploy is the Stork pod. So this is a pod that gets deployed and we've replicated it to 3 instances. And Stork is the storage orchestrator for Kubernetes. So it's part of it's an open source library that Portworx provides. So you can go use Stork and you can go look at it. It's all Apache licensed. But Stork allows us to do a number of other things, which I'll get into in a bit. We also deploy a daemon set for logging. So this is our Fluent bit or Fluent B, whichever one we choose to use. We've got kind of alternated between the two. But this is the daemon set for logging. So all of the containers that land on any of these nodes have a central place on that node to log to. And then those logging daemon sets push to a central Elasticsearch that's our Logstore. So speaking of the Logstore, that's our Logstore. It gets deployed, so it's Elasticsearch. So there's masters. We spin up 3 masters. Each of these 3 machines are on different availability zones as well. I failed to put that in a picture, but first one is AZ1, AZ2, AZ3. So if there's any availability zone failure inside of a region, we have redundancy across other availability zones, and so that's why the masters are spread the way they are. And then our Logstore, we have 2 data nodes, and that's just for reliability in case an AZ goes down, we can still store the logs. As we keep going, we have a monitoring daemon set. So this is the monitoring daemon set that's running to help with the problem stack. And so monitoring is running. Monitoring comes with Prometheus, the Alert Manager, and Grafana. We think it's good enough to run 1 instance of any of those because this isn't part of our mission critical infrastructure. And then we have our ingress controllers, which we've chosen to use Contour. So Contour is similar to Trafic or some of the other types of ingress controllers that are out there. There's a whole bunch you can choose from. We happen to have an enterprise subscription with Heptio, and Contour is the one that Heptio provides, and so we have support for this, and that's why we chose that. We also have a number of REST receivers and other things, and then we have our hot store, which is this is another Elasticsearch instance, but this is the one where the customer data goes into, whereas the other one is for logs. And then we have our cold store, which sits outside the cluster. This is our Azure blob. And then we have our Kafka system. So Kafka comes with its own Zookeeper masters and Roper systems. And we are very carefully allocating so many cores and so much RAM to each of these containers. And so this has been lots of testing, benchmarking to understand how many events per second can we push through a 2-core Kafka broker. The answer is about 100,000 events per second, at least in our testing. And then we have our map server, our stream server, and then a few other internal components in our autoscaler. And so that's the point where on the right, all the core services are laid down for the customer. So when a customer says, enable this application on our SaaS thing, it takes us about 8 to 10 minutes to spin up the VMs. So 3 to 6 VMs on Azure to spin up the AKS, Azure Kubernetes Service, distribution of Kubernetes. It takes about 8 to 10 minutes to do that, and then it takes another 5 minutes to provision our services. So within about 13 to 15 minutes, a user can start using this environment, and it's all completely automated. We have thousands of these clusters running, so there's no way we could ever have somebody go run a script or something. Everything has to be completely automated. And so then a user starts to use the application and they start to configure their user things. So they configure a feed, they configure a real-time analytic, they configure another feed, but this feed has higher velocity. So it is auto-scaled to 3 instances. And then they run a real-time analytic that's consuming that data. Again, it's auto-scaled as well. So these are Spark streaming apps. So there's a driver, and then there's worker applications. And then finally, our batch analytics can run. The batch analytics are ephemeral. So they come, they land on whatever open space is available, and then they go away. And then somebody runs another big data analytic, it comes again, and then it goes away. And so it uses whatever space is still available in that cluster. Does this make sense as a kind of container workload perspective? Any questions on this before I keep going? This is a really geeky slide. So, yeah.
What is the maximum usage that you got? Like, did any time your servers ran out of? Like,
so we have an autoscaler. So the question was, when do we run out of capacity? So we have autoscalers in place for all of the components. That includes nodes as well. So when we run out of a certain threshold of headroom on the nodes, we'll auto-scale additional nodes in. And we scale instances, like the real-time analytics are scaled to 3 in that case. We scale from like 1 to 3 to 7 so we don't just add 1 each time. The nodes we just add 1 because it's going to be an expense to us if we have extra headroom. So we have auto-scalers that take care of all that for us. Did that answer your question?
So do you have any specific load balancer that you use?
So we use the load balancing is quite complicated. So we use the Azure Application Gateway. And so we use the Azure specific components that are there for that. And so when we move to EKS to support Amazon, we'll use those natural load balancers there. So that's part of, when we move to a different environment, those are some of the things we have to change because we are using native services there.
So right now it's a purely Azure infrastructure, right?
Yeah, this picture that you're seeing here is Azure.
Once you get into the hybrid infrastructure, you might, I don't know, you might fix that.
Yeah, so we're okay using those cloud native services. We just, within the Kubernetes cluster, we want to have everything portable. So outside the Kubernetes cluster, like Azure Blob, we would replace with S3. So we're okay changing those components. So our code doesn't change, it's just the configuration. Yes?
So along those lines, do you have any sort of algorithms or whatnot that estimate how long it'll take to spin up new resources based on the time of day and whatnot? Because I know Amazon has some real issues depending on the time of day.
Yeah, the question is, do we account for how long it's going to take to spin up new resources? So that's definitely part of the factor of where we set our thresholds when we spin up new things, because we know it actually, in reality, is going to take a couple minutes to spin up a VM. And so scaling out is easy, scaling in is a bit more difficult. So typically we have people scaling in as a manual operation where operators will see those opportunities. So our alert manager in Prometheus will alert about, there's a potential for scale in on this cluster, and our operator will go make a manual decision about that. And so they'll go in and drain the pods off the node, and then we'll migrate.
Do you have any problems with public clouds in your scale up resources?
So the question is, do we have any problems with our cloud providers limiting our scale out resources? So we are dealing in the volumes that require us to work with Azure ahead of time to say this is our business forecast of how many people are using this, because we're doing thousands of these Kubernetes clusters.
Yeah, that's why the question is because you're doing such a high volume.
Yes.
And it could expand very rapidly.
Yes.
And
yeah.
I heard about a lot of people having problems.
Yeah, so we are proactive about that and have a relationship with Azure, telling them about our forecasts and our adoption rates and those things so they can build out appropriately.
So it's your fault that you're hurting these other people.
Well, if you're using V16 instances, yes. Yes.
This cluster manager that you use to set up all these clusters, is that something you developed yourself? Is that can you talk a little bit how that works?
Yeah, so the question is the cluster manager that manages the other clusters. So the provisioning part of that is fairly straightforward. So we've automated all that. It's all custom stuff that we did. There's no magic there, though. I mean, it's just laying down a Kubernetes clusters in an automated way. To be honest with you, the health monitoring aspect of monitoring 100 or 1,000 Prometheus things is still something that's fairly immature. There's projects out there like M3, the Uber open source. There's Thanos, or however you pronounce that. I don't know. I'm not a Marvel guy, so how do you pronounce that superhero? Thanos. So Thanos and M3 are things that we are evaluating right now. We're doing a bake-off between those two to see which one is better. It looks like Thanos is probably going to emerge as the winner. But those are specializing in making Prometheus highly available, but also having a global view of multiple Prometheuses. And so that's what we're building out inside those environments. So we're still in the process. Yep.
What are your, and determine how much resources are in a cluster? How do you determine the size of the cluster, or what goes into it, or when we should make new clusters?
Yeah, so the question is, how do we choose the size of the cluster initially, and how do we adjust it over time? So we started out the same, so it's always the same 3 nodes that are here, and then we monitor the behavior of what somebody's doing with it. So it's hard for us to know that, you know, somebody's going to go configure a feed, and that feed is going to have 3 million events per second, or it's going to have 3 per day. And so we have to, if we don't have any knowledge about that feed, if they're connecting to things like, you know, the weather or ways or things like that, that are things we've curated, we have metadata about that, and so we can size those appropriately. But when they connect it to their own data set, say it's like a logistics company that has 300,000 vehicles and they're updating every second, you know, we have no knowledge of that, but they connect it to a Kafka system that has that data in it. Our auto scaler component at the bottom of the second node there will monitor what's happening and all those different things, and it'll horizontally scale the feed out so it can accommodate for that. And if there's a real-time analytic behind that, it'll scale those as well. So it's reactive to what we're doing. So every minute we're using moving averages and other things like that.
Is that your own software?
It's our own, yeah. Autoscalers. It's based on the horizontal pod autoscaler, the HPA of Kubernetes. So we just took what they had that's based on CPU metrics and memory metrics and things like that, and we just adjusted it to our own kind of metrics, and we inserted our own algorithms for that. So we've done some pretty sophisticated things with like Spark about, you know, when should we scale a Spark job and those types of things. And it's, I don't know if I have time to get into all the details, but we can talk more afterwards if anybody's interested in that. But yeah, we certainly scale all these things out. That's been one of the bigger challenges, is how do we have good algorithms to scale appropriately. So stateful workloads, let me cover this and then we'll do more Q&A if that's okay. So stateful workloads, we need great resilience of our stateful services. So Kubernetes is good at a lot of things, but it's starting to become better at stateful workloads, but it still has some challenges. And so our assertion of the state of things are that we needed to bring in Portworx as something that would enable us to have the confidence that we could have thousands of clusters running without us having to have our hand on them doing something with it. If we're running like one cluster for our company that did this, maybe it'd be a different story. But with this many things and the automation that we need to have in place, we wanted the assurance that we weren't going to lose any data for our customers. This was a necessary component. So Stork is this really cool stork bird that drives a Kubernetes wheel. I think there's stickers somewhere if you guys want. But it's the storage orchestrator for Kubernetes. I'm an avid sticker collector. If you guys have any cool stickers, let me know. All of the stateful workloads that we have, the tenant monitoring, tenant logging, the hot store and the gateway are kind of the obvious ones. The one that's not obvious, I was going to highlight because I think it's a really interesting use case of this. But we have Spark streaming apps that have state in them. And Spark streaming, again, is good at a lot of things, but it's not necessarily great at state. So Flink and a number of other projects do a little bit better job with state than Spark. But I'll show you how we've solved that problem with that. But before that, a couple other small things that are super important is high availability within a region. So I've kind of talked about this already, that we're using Portworx and as a capability to enable us to not have to do a rebalance on the Elasticsearch piece. Same thing is true for Kafka. So if the Kafka broker goes down, you know, the logs that were written on that Kafka broker are backed by Portworx, and it'll spin up on another node, and then it'll pick up where it left off, and there's no rebalancing or replica reset with Kafka. So those are great benefits to us, and that's what gives us the HA within a region. What we also need to do is to have additional reassurances for enabling business workflows. So if we have a tenant that comes online in June and then they say, I don't want to subscribe anymore, I'm going to go offline in July. We don't want to run 6 nodes for them in July to preserve their workspace. And so what we do is we actually snapshot the entire state of the cluster. And so, you know, snapshotting is something that's traditionally done at each component level. So I'm going to snapshot Elasticsearch, I'm going to snapshot Kafka. What we've done is we said, we got too many moving parts to this thing. Let's just snapshot the whole cluster. And that sounds kind of aggressive, but that's what we did. And we're using a project called Valero to do this. It was formerly Heptio Arc. And Valero allows us to snapshot the entire state of a Kubernetes cluster at a moment in time. And what that enables us to do is we can actually take that snapshot, put it in cold store, Azure Blob in this case. That Azure Blob is available for us, that if anything happens to that cluster, we can go restore from that point. So we're on an hourly snapshot perspective. What this gives us is disaster recovery as well. So if the West Coast fell off the face of the earth, as I talked about before, they could take that Valero snapshot, somebody on the East Coast, and put that on EastUS2, spin up that tenant, and maybe there was 30 minutes of downtime, but we can restore that cluster where they left off. And so I think 30 minutes of downtime, if the West Coast fell off the face of the earth, is probably okay for that tenant. And so that's what we have in place. The other interesting thing is if the tenant unsubscribes in July and they decide to come back in October, all we are keeping for them is a little bit of storage on Azure Blob, and we can go rehydrate a cluster for them based on where they left off and pick up where they left off without incurring much of a cost at all other than just a little bit of Azure Blob cost. And so that's a huge benefit other than saying if you want to come back in October, then you got to start all over and you lost all your data. So that's a better thing for us. And then the last thing is, it's kind of a side effect of this is, yeah, question.
Two quick questions.
Yeah.
So when you say tenant, you mean like customers such as cities,
Yeah.
correct?
Yeah, like City of Atlanta would be a tenant to us, yeah.
The second question is how often you are doing this, the Valero thing?
Once an hour.
Once an hour.
Yeah, we try to do it quicker than that, but the amount of time it takes to copy, because the Azure Blob is, we turn on geo-replication because we want it to be in the current region, but also a geo-replicated region. So the amount of time it takes to copy, and you can imagine all the stuff we have to copy terabytes of data, it takes 20 minutes sometimes for that to happen. And so until that becomes faster, we have to keep that at about an hour. So that's our SLA. Yep.
So is Valero like a free service or is it a paid service?
Valero is an open source Apache project, Apache license project from Heptio. VMware now, I guess. They were acquired by VMware. Yeah. So what's interesting though is the capability that I'm describing of Valero in the next version of Stork, which comes out in the next couple of weeks, does the same thing. So we're actually looking to remove Valero and just use Stork to have one less moving part. Yeah.
Can you write your automation to build up a cluster inside of a cloud provider?
What's the automation?
What is it written in?
So
Is it like Terraform or?
So we have just a bunch of scripts that do it in Azure. So we're generalizing it now into Terraform so that we can do it across multiple cloud providers. And then we can even do it like on premises as well for customers that want to do that. So yeah, Terraform.
Use Helm or
Helm charts are predominantly what we do for everything. So everything is put into a Helm chart. And if there's an operator, the Helm chart's deploying the operator. Question?
So Valero does snapshot of the persistent storage or is it for?
It's the whole cluster. It's magic sauce. So you look up Valero and take a look at the project. It's really cool, and it's really cool that it's open source too. But it'll snapshot the entire state of the Kubernetes cluster. So it snapshots the masters, the configuration, the containers, what's running, what workloads, how many instances, how many replicas, and then the actual volumes. So if you've configured things with persistent volumes, those get snapshotted as well.
It does clone as well?
It does what?
Cloning as well, or is it just a snapshot?
Well, it's like a snapshot of the entire state of the cluster. So technically it is a clone at that point in time. Yeah, so then you could restore into another Kubernetes cluster somewhere else.
It's something like ESXi does it for VMs. You use ESXi.
Beam backup?
Yeah, so in the disaster situation, it won't work because the snapshot will be still on the US West 2.
No, so the snapshots are geo-replicated.
Okay, that's
So Azure Blob's geo-replicated to central somewhere, I think. Yeah. So, and the point earlier too is Valero, the same capability is going to be in the next version of Stork. So we're getting like an early version of that. That's part of the reason I was here this week was to talk to them about that, to make sure it does what we need to. Yeah.
So just to add to this question, so is it like stops over an operation?
Say it again?
When it does a snapshot, it stops?
No, so it'll still enable everything to run. So it just snapshots whatever it can at that point in time. So data's still flowing through. Yeah, data's still flowing. Everything's. I don't need to like suspend containers or anything like that. Yeah. So it's really nice. But you know, we're using a combination of Valero and Stork. Stork being like the volume backups to do it. The persistent volume stuff probably wouldn't be as good without the Portworx stuff. So you know, test that out and see for yourself and see if it's good enough for what you want. But we need to have the Portworx piece as part of our equation.
Sorry, one last question.
Yeah,
How
sure.
often you guys do disaster recovery testing?
Disaster recovering, so we do it at least once a month.
Okay.
And so when we were in development, we were doing it like on a weekly basis. So this is, again, the list of analytics. The one that I didn't really highlight was this Geofence features, which you saw in the demo. So the demo was just tell me, filter the data that's inside Bahamas or Cuba. But what if I wanted to know when Adam entered this room? So if I wanted to know when Adam entered this room, I need to know my last position and my current position. So there's some state that I need to keep, what my last position is. And so that sounds like an easy thing to do, but it's actually not an easy thing to do in Spark Streaming. So Spark Streaming doesn't really give you, that's the Spark Streaming is the purple box there. It doesn't give you a way to do state very well. And so if I want to do, you know, tell me when the vessel enters a no fishery zone or exits a port boundary, I need to put a sidecar passenger with my Spark Streaming app, and that sidecar passenger is the state. And so with the more recent versions of Spark Streaming with structured streaming, there actually is a state model, and you can use that state model to do some of this. But it suffers from one challenge, and that challenge is a Spark Streaming job has a driver and it has n number of workers. And so let's just pretend for simplicity there's one worker. So all the data is going to that one worker. As data starts flowing into here, if I have track one that comes through, I keep that in memory. Now, that's the first observation I got for track one. So I don't know if he entered or exited or not, because I don't know where he was before, but that's the first point in time, so that's okay. So as data keeps flowing in here, I can detect if they entered or exited. And now when I get a second point for T3, I can detect that he entered, and I can keep going through this workflow. And so this works quite nicely, except for the bootstrap section. And so what we want to do is limit that bootstrap section. So the very first time you ever deploy this analytic, you're going to have the bootstrap. But what we don't want is that when there's a failure, like this worker dies for some reason, we don't want the situation where it comes back and we have to go rebuild all that state again, because we're going to miss the enter-exit events. And you might be saying, well, is that really that big a deal? Well, if we're tracking a bad guy and it's an intel agency that's using this application, yeah, it's a big deal that we missed that he exited a building or something. So it's super important to some of our customers to do this. This has been a problem we've never been able to solve. We've had this real-time GIS concept for 6 years now on premises, and we've never been able to solve it. The way we solved this was a unique way of actually attaching a persistent volume to the Spark Streaming job and backing that persistent volume with Portworx, so that when it comes back, we rehydrate the data for that. So it doesn't matter what node it lands on. If it lands on a node where there's a replica on Portworx, it'll rehydrate the data from where it left off, and so we won't miss those events. And so we can finally solve this new problem. So I presented this one in detail because I think it's kind of a novel approach to using persistent volumes, because you typically wouldn't think about using persistent volumes on Spark Streaming. So the way this works is Spark Streaming will checkpoint, and traditionally Spark Streaming checkpoints for the purpose of keeping its consumer offsets to Kafka and other things in sync. But in this case, it's actually keeping application data in there. So this has enabled us to actually enable other types of analytics in real time as well. So last slide that I have is on auto scaling, and I think some of you have asked some questions about this already. So we need to be able to auto scale the storage aspect of things. And the storage aspect is both, remember we attach a 1 terabyte drive to the node. That's what we've chosen as our starting point. And whatever containers land on there, if Elasticsearch data nodes and Kafka brokers land on that node, they're going to use that volume quicker than later. And so when we hit a 50% saturation rate of that volume, we'll dynamically grow that volume as big as we can to 2 terabytes, and then we'll add another 1 terabyte volume on there. And then we'll do that for up to 8 terabytes. And then when we hit 8 terabytes, then we actually have to go through a process to add another node, add more volumes onto that node. So there's a point of saturation and diminishing returns on that.
Does the additional volumes, do they have to be on that node or can they be someplace else in the
So
system?
they could be somewhere else. Technically, the way we've decided to deploy it is to have them on the node close to where the work is happening. So you could have a node that was a very
Is that sort of wasteful though? Because you don't know how much you would need to expand, so you have to have all these hard drives on that node. That this doesn't seem right to me.
Yeah, so we're actually doing it dynamically. So we start off with 1 terabyte, which is fairly modest for the data rates that we're going to have. And then as data accumulates, we dynamically add additional volumes on. So we're not having 8 1 terabyte drives on there initially. We grow as we need to and the application need arises.
So what you're saying is that you would replace the 1 terabyte disk with a 8 terabyte disk?
No, we have 8 1 terabyte disks. Yeah. So we add a 1 terabyte disk every time we need additional volume, and then
Oh, you just plug it in?
Yes.
Oh, okay.
Yeah, and the node doesn't have to go down. The containers don't have to stop. It just dynamically allocates it, and suddenly there's new space available. Yeah.
But doesn't that sort of reduce your automation? Because you got to have a human being to.
No, it's actually automated. Yeah. So Portworx is providing us that capability. So there's this autopilot.
How do you increase the disk in the node, except if a person doesn't plug them in?
So we get a signal that the disk is hitting up from Portworx, and then we have automation in place that attaches another managed disk to that node.
I think the disk is a disk that is provided by Azure, right? So that's not hardware that someone plugged in.
It's a piece of hardware, another 1 terabyte disk that we tell Azure to attach to that node, and then our persistent volumes are software-defined storage usage.
So the storage may be different than the actual node. A different place in the actual.
Yeah, so we don't actually use the local disk on the node at all. So we only attach disk to it, and we use that as storage. So the VMs that we've chosen have very small local disks anyway. Yeah, good point. Yeah. Okay. So there's this resizing of the volume, and then there's also the pool resizing. So the pool resizing is adding the second, third, fourth 1 terabyte nodes. And then we also have auto scalers for nodes. So we talked about this before. So upon a pod request becoming unschedulable or even sooner than that because of the 2 to 3 minute startup time, we may scale out. And then item pods and service pods get scaled out as well. So that's where a lot of our custom logic is. So that guy is an internal Esri project guy. So that's not an open source project. But this is the custom horizontal pod auto scaler logic that we wrote for our specific application use cases. So I think I'll stop it there and take any questions or answer.
And before we go open to the Q&A, a couple of things. And also I want to, oh, sorry. Did you get your pictures? Okay. Everybody wants a picture of you. Oh, that's your Twitter address. Okay, I need to retweet. Sorry, I live tweeted the whole thing. Tagging Esri and not this. I'm going to open real quick on the phones and see if anyone who hasn't been able to ask a question and just give it out to the phones because hello world, we have a lot of people out there. So let me take the first couple of questions to the phones if there are any. And I want to give a shout out. Sean, I see you're in the house. We have some celebrities who tuned in all the way from Canada, journalists and fun people. So thank you, Sean, and all the other folks that came online. And let me just open, hang on, I don't even know how to do this. I probably should have asked FunCat. Oh, unmute all. Okay, by the way, everybody's unmuted right now, so everybody be good. I think everyone's unmuted. Okay, maybe this technology doesn't really work.
Sorry. It came up online. So.
He rigged it because he wants to be my knight in shining armor. He wants me to owe him one tomorrow. He's going to say, remember when I saved your hide during the meetup? And I'm going to have to do some like engineering
I think this person
favor.
is muted himself, so we can unmute him.
Oh, I see.
Yeah.
Okay.
Yeah.
All right. Sorry, world, you're on your own. Anyway, everybody else. Everybody else. And well, first of all, thank you, Adam again for coming all the way up here and repeating the questions for, you know, everybody. Like, I didn't even ask him to do that. He's such a pro. That was so awesome. He like repeated the questions and giving Stork a shout out. It's also one of my favorite open source projects. And I will put Stork stickers out there for you to take on your way home. So thanks for the Stork shout out as well. Dinesh was here earlier. He really gets a huge round of applause for creating and open sourcing Stork. If you met our engineer Dinesh earlier, he's awesome. Anyway, so okay, we will go on to the Q&A, but just can we get Adam a round of applause here? So much. Thank you. I'm going to put out a little bit more beer and wine, and you can go ahead with the first question.
Two questions. First, the on-prem architecture, is that a replica of what you have there? And you run? It's very completely different.
Yeah, so on-prem we built like 6-7 years ago. And so it's a traditional like server, you know, here's a disk installed on your machine type of thing. So we want to bring the same architecture back on premise, but we're waiting for the industry to catch up. So we're waiting for, the way we think about Kubernetes is it's like, to me, it's like the Linux kernel. So we wouldn't go build an app for a specific version of Linux kernel, but we would go certify our app on Red Hat or Ubuntu. And so to me, you know, we can't just go tell our community base or our user base to, you know, install this version of Kubernetes and good luck. They need a distribution and they need a support model that they can go grab a neck of, so they're not grabbing my neck. And so we're waiting for a good on-premise distribution to emerge, if that's OpenStack or something that VMware creates or something else. So I don't know that that exists today.
And so in the meantime, you sell still both on-prem and or?
That's correct, yeah. So we still sell the on-prem product and that'll meet the needs of certain customers. And then we have this architecture that people can choose to use, and we're completely fine with cannibalizing the sales of our on-premise software in the meantime. So it's actually more cost effective for us to deliver the SaaS and manage the SaaS than it is for us to manage the on-premise. And it's actually more cost effective from a pricing perspective for a customer to use the SaaS. So we want them to use the SaaS.
Hi. First, I want to compliment you. You're an excellent speaker.
Thank you.
I attend a lot of meetups, and you are right on the money. Second thing is for the on-premise off-premise, why don't you use hybrid, like Azure Stack? And
yeah, so I'll repeat the question so I keep my good status here. So why don't we use Azure Stack or any of that for on-premise? So it's a function of what our user base is willing to do right now. So our user base right now is running like Windows servers and Linux servers, and that's what they're used to doing. And they don't even have Kubernetes administrators on site with them. So think like you know, where are we at? San Jose. So San Jose Police Department, right? Probably not going to have a Kubernetes administrator there. So, you know, it's not, or they're not going to have Azure Stack there, but they have a Windows server that they could run a basic app on. And so that's what the current state of the art is for them. What we're trying to do is commoditize this whole thing and give it the simple button and let people go to our SaaS and just do this. They get all the robustness of Kubernetes, but they don't need to know anything about it. But we do have customers, like large logistics customers, financial customers, folks like that, that want to run this on-premise. And so we plan to deliver the stack on-premise once there's a proper distribution we can certify against. Does that answer your question?
And follow up on the storage part, any need for tiering or hybrid storage? You're doing HD, you don't care, you do SSD for persistency, for performance, any of these things that you're looking at?
Yeah, so the question is what type of storage do we consider when we're doing this? So we're using Azure Premium managed disks for everything. So it's basically equivalent to like an SSD. It's equivalent of speed like a local SSD. But it's attached, and we have all the benefit that we talked about before. And for on-premise things, we would suggest, you know, similar type of structures for that. So that's part of what we need to figure out for on-premises is how that part of the stack works. So how does Portworx and attached disks and all that kind of work with an on-premises environment, and what do we expect our customer to do in that case? Whereas we can completely do it with software definition today in the cloud. So.
And is latency an issue? Do you do any edge-related activity?
So the question is latency an issue? So when latency is an issue, we tell our customers to partner with like an Amazon IoT or an Azure IoT, where they're using Greengrass in Amazon or Azure IoT Edge type capabilities. So with that, they can actually put the logic in the edge. So it's doing some of the compute. We don't have There's another whole thing called KubeEdge. So it's Kubernetes at the edge, but it's a lighter weight version of the kubelet implementation is the lighter weight version. And so as that's emerging, we're very interested to actually put these same workloads on the kubelet infrastructure on the KubeEdge. And so that would enable us to actually deploy parts of our software on the edge being, you know, at a cell phone tower or possibly inside a car. And so those are areas that over the next coming years, I think will emerge as new opportunity spaces for us.
You can do any machine learning or any intelligence into your...
We do a ton of machine learning and that type of stuff. We have a whole initiative called GeoAI. So GeoAI is a partnership that we have with Microsoft. And so it's a joint thing with their Azure ML and then the GeoAI type of stuff that we have. And so we enable that as a good kind of pass between where you could do Azure ML, you could do some Geo, and then you can do Azure ML again. And it's not, we always position it as Azure, but we do the same with SageMaker and other things as well. So, yeah.
Just curious what percentage of your customers is on-premise versus cloud?
Yeah, so we are just launching this service as we speak. So it's, you know, predominantly on-premise, and that's been traditionally our stack. So as we roll this out, we expect thousands of tenants to roll out on this, so they're not deployed yet. So we have early adopters engaged in this, and we're getting great feedback from them. It's functionally meeting their needs. We're operationally getting prepared to roll this out. So our rollout is in October timeframe. Sorry, I should have mentioned that earlier.
So on that rollout and what you're seeing, are you seeing the change in distribution of your customers? Like I would expect that on-premise are going to be larger customers with a larger revenue, and I'm wondering if you're seeing more mid-sized or smaller enterprises.
Yeah, so the question is, how's the distribution of on-premise versus SaaS customers happening as we roll this out? So to be honest, the on-premise distributions that we have today are the more advanced customers. And so we're missing a big market opportunity with the customers that aren't willing to deal with that complexity. So when we say, you know, here's Realtime GIS to our customers, they all get excited, and then we talk to them about the reality of you need a machine to do this, another machine to do this, and 3 more machines to do this, and they're like, yeah, never mind. And so, you know, we're going to hit a whole new class of customer we've never hit before with this new SaaS, but we're also going to convert a lot of those advanced customers that are just sick of dealing with the complexity over to this as well. And so even some of the advanced customers that we have, we can't meet their velocity throughput needs with our on-premise product. We can only scale to about 50,000 events per second with our on-premises product, whereas we benchmarked about 3 to 5 million events per second on this new SaaS offering. Actually, we haven't hit the upper limit, but we stopped testing at that level because I don't know of a customer that has velocity higher than that. So, and that was like an autonomous vehicle type use case where tell me when this car goes over a slippery condition, and if there's 2 cars behind it that hit the slippery condition within 30 seconds, tell the future cars to change lanes. It was that kind of use case. So, yeah.
You mentioned that all the provisioning, like the allocation of disk is all automated, right? So why would you have a threshold of 50%? I mean, doesn't that seem to be like really low?
It's just so the comment is, why is our threshold 50% for when we spin up another disk on there? So it's just a safety thing. So depending on how fast the velocity of data is coming in, it might fill up quite fast. And so we don't want to ever be in a situation where we lose data for a customer. And so there's potential that we could lose data if that disk didn't attach quick enough. So, and it does take some time for that attachment to happen. So,
how did you handle all the high velocity data streaming that is coming in?
So the question is, how do we handle the high velocity data streaming that's coming in? So, so we have feeds that sit at, so typically those really high velocity, millions of events per second use cases are Kafka systems that we're connecting to. Yes. And that's really the only transport that we can use to handle that type of rate. And so we sometimes go direct Kafka to our storage system, so we can bypass a lot of instead of having a feed and a real-time analytic, we could just go straight to storage. Or if they want to have some real-time analytics, they could do that, but those end up getting horizontally scaled as well. So it might be a Spark streaming job that has 20 or 30 workers, associated to it instead of just like one worker that's traditionally handling.
How many different lines do you have coming in to handle that?
So we have, on the feed side, we have about 50 different, you mean like internet lines or?
Yeah.
I don't know, that's Azure stuff. So we just use the Azure line. So I don't know where the customer's bringing in the data to their Kafka, but we just connect to their Kafka and use the connectivity that's there. So we haven't had a pipeline capacity problem with that. So we have like an insurance.
Yeah, some kind of queuing system going.
Yes, Kafka is the system. So like we have an insurance agency that is doing like behavioral modeling of, you know, if you're driving your car well, you get a better premium that week or whatever. And so the people that opt into that is one of the high velocity use cases. And so there's a Kafka system that's even on premise inside their environment that they've opened up special ports and other things and security for us to do that. That's been a challenge upon itself to figure out the security around some of those things.
Yeah.
But that's
my next question, you know, security.
Yeah, security is very challenging in this environment. So the easiest thing we did to help security was that we isolate, every tenant gets their own Kubernetes cluster. So that's as isolated as you could possibly get with this. A lot of people are doing one Kubernetes cluster or multiple namespaces for tenants. And that's another
You might have multiple clusters per tenant though, right?
We won't have multiple clusters per tenant. Yeah, so there'll just be one cluster until we hit the bounds of how big a Kubernetes cluster can be, which is about 2,000 nodes right now. We've only tested up to 300 nodes, I think, but that's well beyond what any actual user is probably going to do. So,
yep. We have our own say Kafka clusters, Cassandra and Spark. Would we be able to leverage your platform, ArcGIS platform, or do we have to feed you all the data?
So we can connect to a Kafka system if security could be in place for us to connect to that, if that's on premise or if it's in the cloud, or if you're using what's Amazon streaming technology, Kinesis. You know, if you're using Kinesis or you're using Kafka as a service on the cloud or things like that, we can connect to any of those types of systems. So that's typically how we've done it. Did that answer your question? I mean, Cassandra, we're not going to connect to your Cassandra necessarily, but we typically are streaming data in and getting events. Our batch analytics can connect to Hadoop systems, specifically HDFS. So if the security is in place, we can connect to HDFS, we can connect to Elasticsearch, we can connect to S3, Azure Blob, and a couple other things like data lakes and things like that. But we haven't built connectors for Cassandra and data stacks and those things yet. So. But as we see demand, we'll be adding those.
So for example, if we build our own ML engine, so if we leverage some of the analytics, would we be able to deploy your cluster, or do we have to keep it?
It's kind of a complements next to kind of situation right now. So we wouldn't embed your workflows in our stuff, but we could sit next to yours and we can integrate through a streaming technology or one of the storage technologies that I mentioned.
So I'll take one more. Is it a quick question?
Yeah.
Okay, and then we're going to wrap up. And I want to still let you have your Kubernetes questions to other experts that are here too, and you can mingle over there. So we'll take one more question online here, and then we'll close it out. It's quick.
What type of networking you're using for the clustering? Is it Calico? Is it LAN?
So we're using the default Azure VPN technology that's in there. So we've had to give it a couple special switches when we spin up the AKS cluster to have certain networking things enabled. I don't remember exactly.
I think he was asking about, you said Contour, right?
That's the ingress controller. Yeah. So we're not using Calico or anything special like that. So we're just using the built-in AKS networking. But we did have to give it some special switches to make it perform better. So I don't remember exactly what those were.
Okay. All right. So I think we commissioned Adam. I'm totally joking. He's been so nice this time. I think probably be here for another 9 minutes at least. There's a couple more. There's spears. There's t-shirts. I put some Stork stickers out there that he referenced on your way out. And there's a couple, if you see people in Portworx shirts, you can also ask them questions about Kubernetes for about another 15 minutes. Put another bottle of wine out there, and then we can wrap. Can everybody give Adam a stick that? Thank you. Oh, thanks, world. Catch you next time.